okay? And for many years, he has been working in problems related to statistical physics, especially percolation problems, computational fluid dynamics, transport problems in disordered media, optimization problems related to transport in various applications. But for the last few years, he has turned to the dark side of the force and started working on machine learning and artificial intelligence. And that's the subject he will talk to us about today. So please, Professor Andrade.
Okay. So can you hear me? Yes, I can hear. So good afternoon. I first would like to thank the organizers. Thank you very much to you two and to others. It's a real pleasure to be here again. I have been here for the last time, 2019. I think so, before the pandemics. This thing was still working, yes, 19 years. This machine was still working, very robust. It's resilient stuff. No? Anyway, so as André, who was my former undergrad student in Fortaleza, I was telling people that he was the best former undergrad student I have ever had, yes. So he didn't like this, he didn't like praises. Yes. So you pay me a beer later on. So, anyway, so as he said, I come from Fortaleza, Universidade Federal do Ceará. I have many sponsors. Don't think that my salary is proportional to the number of sponsors. It is not. And I'm going to talk from correlations to interactions, application of a maximum entropy model to finance. Originally, the title had to finance and neuroscience. But then Mauro Copelli came here and gave 3 classes, no, about neuroscience, and he simplified a lot my talk because the first and the second class are mostly about the works made by William Bialek on the machine learning and Boltzmann machine learning models, which I'm going to use here. I'm doing a spoiling, but I was going to use for this finance, which is a very strange subject, as well as neuroscience. Then I decided to remove the neuroscience because there was already a lot of discussion about that. I saw the movies of, because he already released some of the videos of this conference, and Mauro gave a very nice talk, and excellent. I learned a lot, and I have to adapt. So instead of only talking about finance, removing neuroscience, I will give you a bonus. So So I'll try, if I have time, to talk about digital contact tracing and network theory to stop the spread of COVID-19. It's an old theme. People are already bored about COVID, but it's interesting because we are doing it for other things. If I have time, I will talk about that as well. Okay? So first, the team. Humberto Carmona is a professor in our department. Hilder is a professor at Universidade de Fortaleza. Saulo is a professor in our department. Cesar is a professor. And Igor is a PhD student working under my supervision in Fortaleza. Okay, so the first thing is the data. As André said, the data is what we call in Brazil nota fiscal. So it's digital invoices that people use. And we were talking about what companies use. We are not talking about physical persons. So companies exchange products between themselves, buying or selling, and through this type of document. This is a typical example of a fiscal note or electronic invoice data. It has 43 fields in it. For instance, you might see the field which is respective to the name of the company that emitted it, to the name of the company that received the product. This is, of course, not allowed for us, was not allowed for us to know these names. Otherwise, we could, you know, they are preoccupied about how to use that. This has been duly anonymized. But we do have the date of emission. We do have the city where did it come from, where the city where it come from and where it went, the municipality as well, the value, of course, and as well as the type of the product and the activity, economical activity. So it has, we have data from 2010 to 2020 from the Finance Secretary of State of Ceará, and this accounts for something like 6 billion invoices, which one has 43 fields each. So It's a lot of data. So, of course, at the beginning of this project, we thought we could work from 2010 to 2020, but the 2010 to 2016 was not very well implemented, so we had to filter and clean the data a lot, so we decided to fix our attention in 4 years from 2016 to 2019. Anyway, so first of all, I'd like to show you how these invoices move from one city from one municipality or city to another. So I would like to give you an idea of the movement of these fiscal nodes, and of course, the macrodynamics of the economy in the state of the Ceará. Okay, I think it will activate, no? No. So this is more or less like that. So the arcs, this is a directed lattice network, if you want, which evolves with time. The total amount of resources that are involved in this are computed here a long time, as you can see. So it fluctuates a lot. And the color of the arcs, which go from one city to another, correspond to the amount of money in millions of reals that are sending from one city to another. And this is a daily sent that we did. So eventually, we ended up, this is disturbing, I'm sorry. Eventually, we found the pandemics, and we could see this V of the pandemics here. So there was, and if you make a zoom, you see, you go to the region, to the metropolitan zone of Fortaleza, which is the capital of the Ceará state, and you see that the most important cities in the financial market of the Ceará state is Maracanaú, Caucaia, Fortaleza, and Eusébio, which André Vieira, as a good Cearense that he is, knows very well these municipalities, no? So, anyway, so we wanted to study this, and perhaps do some physics on the top of that. Let's see if it's possible. So first of all, it's interesting. Why? Because the Ceará state it doesn't look like when you see the entire Brazil, it's a large state of Brazil. It's almost of the size of Greece and Nicaragua. So it's a large. It has more than 10 million inhabitants. So it's a large state. So, and it's a very long, very large area. It has a very uneven wealth distribution, so it can be very poor or very rich, mostly poor in most parts of the state. And also, it has very different densities of populations for different municipalities. So working with the entire state is already too macroscopic for the type of things that we want to do. And as well as we would have to stratify it a lot. So we decided to use this data to try to find macro regions of finance. And to do that, it's possible to use different algorithms that are available in the literature to calculate modules which have some cohesive interests. Okay, so we started with the classical one. First of all, we are talking about 184 municipalities, which are the sites of this network. This network is a directed site. Why? Because one municipality will sell and the other one will buy. The direction is from selling to buying, and the weight is the number of transactions or the amount of money that has been used in that transaction. And the period is 2016 to 2019, as I already said. So we used a stochastic block model, which is a generalized modularity algorithm. And this algorithm identifies models based on the structure of the network itself without accounting on the flow, any type of flow. It doesn't know the dynamics. Okay? So when you do that, you see that you can somehow find more than 20 macro regions. So these macro regions don't have contiguity. So they are not connected altogether. You see holes of one macro region in the middle of another. So the structure itself, based on the fiscal nodes that has been envoyed, doesn't allow this algorithm to capture the macro regions in a financial way that we want. So instead of doing that, we decided to use a different algorithm, which is the InfoMap. The InfoMap is an algorithm that uses the concept of random walk, in a very sophisticated way, so because you had to do some transformations. I will not go into the details of that. But basically, it finds modules in a network by minimizing the length of a random walk movement inside of the system itself. It was proposed by Roswell and Bergstrom. This is a very important paper in this field of modularity. It was published in 2008, and I think it has more than 6,000 citations so far. So the network will be compacted if regions are identified where the walker tends to remain for a long time. So where the random walk stays for a long time will be most likely related to a module. And it captures the network optimal community in this way. So when you use this to this directed network with weights, that's what you find, much more stable and reasonable type of division in macro regions. So we found basically 5 macro regions. The first one with 78 cities, which is the blue one, 53 cities, the orange one, and so on and so forth. But more than that, you don't see pieces with holes inside, which in mathematics has a very specific name. So they are simply connected modules, okay? So it gave us some confidence that we could go and divide the system mostly because of the consistency in terms of this algorithm, as well as because we wanted to do that to understand what we want to use later on in terms of machine learning. So if you put in a line, if you want to see the correlations, the trade share matrix between one city to another, this is the type of matrix that you see. Of course, this matrix is non-symmetrical. Why? Because we are accounting for selling and buying. Well, you can see that Fortaleza, which is the capital, has a very long range with all the cities in the state for selling as well as for buying, and other large cities also do. So you find that this system has very strong correlations within the communities. So, but this algorithm was able to separate them and put Fortaleza in there in a single one instead of mixing everything. So we were happy with this, and then we decided to go for the next step. Once we have reduced the dimension of the system to 5 modules, now we can try to understand what's going on in terms of the portfolios of every city that we have. To do that, we used another concept which appeared in the literature, and this concept was developed by Hidalgo et al., published in Science in 2007, a physicist, economist, working in econophysics. What did he do? He calculated the revealed comparative advantage index, which is basically this fraction of fractions here. So where K of MP is the monetary value traded by the CTM of the product P, and RCMP is the revealed comparative advantage, as I said, of the CTM with relation to the product P. So I have to write down everything because my memory is not going on. If I try to explain everything using my own words, it will be confused. So the numerator corresponds to the relative selling or buying. We have to divide selling and buying. There are 2 different categories. Value of the product P by the CTM compared to the sales of all products by the city. This is the numerator here. So it's only related to the CTM itself. It's a local fraction of the importance of that product. And the denominator is the global importance of that product to the entire state. So it corresponds to the relative value of all sales of the product P in the entire state itself compared to the all products. So when you do that, you calculate, when you divide one by the other, you calculate the RCA, and if this value is larger than 1, it means that the product P is relatively more important to the trade of CTM than the relative importance of that product in the entire state. So the average in the entire state compared to the relative importance of the product P for that particular city is smaller than 1, or RCA is larger than 1, the opposite. So in fact, what we are doing here, which is very important in a way, because we want to remove population and other features of this problem that might cause bias. And what you're basically doing here is that calculate an index which is essentially a demonetized one. That's the basic idea behind that. And it also imposes a threshold, a binarized way to do this. So binarization is the key word for this particular case here. So we can binarize. So when you do that, so this is what we find. So we can also create something based on that. And we're getting
sorry,
to...
can you come back just
Yes,
one slide?
yes.
How can you have this RCA smaller than 1? It seems that you are dividing by something which is always bigger, no?
No, but this is an average because the denominator is dividing. The denominator of the denominator is dividing the sum of all cities.
Okay.
All M.
I see.
So it's a sort of average for all cities. And then you compare the average of that product, local product, compared to its own average, to the average of all other products. Is it okay? Okay. And now you can you can start to realize what I'm going to do now. So we have a binarized, so we can define some sort of activity of the CTM with relation to the product P, relating that with our RCI in a language that we know more, spin language, for instance. So sigma of MP is equal to 1 if RCA is larger than 1, and equal to -1 if RCA is smaller than 1. And then when you put dots, which are blue for 1, and which are white for -1, and divide into the different communities that we found here, this is the scatter plot of the cities, which are in the vertical line, and the products, which are in the horizontal line, for buying. Okay? So this is somehow how these products are relevant for different cities in a different way. This is for buying, and this is for selling. So, but before, I also categorized, just to make it more adequate, we can also always calculate the diversity of the basket of products for selling of a CTM by simply summation the activity +1, so that we always have a positive number. And then what we do here, we plot this in the descending ubiquity, descending peak frequency. So as whiter it becomes, those products which are in the whiter zones are less important, okay? These zones becomes less important if it's less populated. And also the ubiquity for selling, buying, or a given product in the basket of the cities, which is the line in this direction here. But now we are dividing it for regions, goes in this way, just for your information. Okay, so there is no time here. It's just a ranking way to do that in terms of diversity and ubiquity of the product and the municipality itself. So when you do it for buying, for selling, you have this, which is, as you can see immediately, is much less denser than the selling one. So why is that? Municipalities and their inhabitants, of course, like we live in a city, we purchase a wide range of products that satisfy our quotidian life. So, but usually these products are not produced locally, although they are being there. So this is why the buying thing is much denser than this one. Why? Because on the other hand, the production of that city, which makes that city sell something, is very much more specialized. So it focuses on the specific products, and the factors that depends are the availability of the resources of that particular city, specialized expertise of the city itself, because it will depend on how people do that, and labor considerations, as well as historical and cultural effects. So this is why the buying raster plots are much denser than the selling raster plots. This is a qualitative feature. Anyway, but now, what do you have for a given one? Let's isolate the largest community here. What do you have here is a city, as I said, in the Y direction, the product in the X direction. And if you make a zoom, you see simply numbers +1 and -1, corresponding to the blue and to the white spots, respectively. So, basically, if you want to understand now this in terms of a state of a system, a product itself and the way it appears for each city can be quantified, can be understood in terms of the state or configuration, the phase space of that product. Okay, so this would be the state of the system for a given product. And the cities themselves are going to be the spins. And when you do that, you can calculate, for instance, the magnetization of that city by simply summing up all the activities along the line of products that it has. okay? So this is the average magnetization. I am already talking in terms of magnetic properties now. So this is the average activity of city and overall P products. And now you can also compare two different things. And then you can, instead of calculating only the magnetizations, you can calculate the correlations, which are other observables. So if you compare CTN with CTM, you can make a pairwise correlation between them along all the products. And then you have to remember these are observables and real data. So this is all we have in terms of sampling for that particular system. Okay, so now we want to do some statistical physics on the top of that based on these observations, as Mauro explained well. Okay, so what do we do here? So from correlations to interactions, we have correlations, which are the observed data, and we want to transform them into interactions. You have to understand that I'm putting quoting marks everywhere on this. Interactions with quoting marks. Okay, so this was a paper published by Bialek. So our observables corresponds to average activity and pairwise correlations. So these are the two constraints that we might use in the calculation of our Lagrange multipliers. Okay, the overall magnetizations for each city and the correlations between pairs of cities. Okay. So as I already said, we denote sigma vector as the state of the system of the m cities passing through the product P. Since every city is one or of the two states minus one, overall we have 2 to the n. M is the number of municipalities, possible states in that system. So we have only a sample of that because in our case we have 1,600 products. We don't have the entire phase space. Okay? But we have some observables. So given that the constraints 1 and 2 for all M cities, the distribution that maximizes the entropy, which is this one, the Boltzmann one, with the normalization for the probability itself, is simply this one with the partition function, exponential, in terms of an age. And you can show by calculating explicitly the Lagrange multiplier based on these constraints, as well as this one here, that the Hamiltonian, already under quoting marks, is an Ising-like Hamiltonian. It has no physics up to this point at all, apart from the, of course, the Boltzmann entropy that we are using with this partition function. Look, I didn't put temperature at any point here. This is something that we have to use later as an analogy. So it's an Ising-like model from real data. So that's how you derive it. Okay, so you can rewrite the equations like that. And of course, you can use Kullback-Leibler type of expansions to see what would be the way to find these parameters. Now we have, I forgot to say that the parameters that we have are something like local fields, as well as couplings between different states, different spins. Okay? And as Mauro Copelli said, well, the number of observations that we have matches exactly the number of parameters that we have, but they are not the same thing. The first one corresponds to correlations. Now we have Lagrange multipliers that will be interpreted as interactions eventually, if we can. Okay? So this is called Boltzmann machine learning for some people, but others also use the same nomenclature for different techniques, slightly different techniques. So in practical terms, we don't use the Kullback-Leibler equations. We use typical algorithm to find out in the core of the system we have to calculate. You have to use a Monte Carlo in the core of the system to calculate the parameters and updating them in a sequential and simultaneous numerical sequence. Okay, so we have to do some sort of algorithm to calculate based on an initial guess, and see if the age of M for each spin or each city and J of Mn will eventually converge to something which is stable. And then, of course, you have to understand that every time you calculate one iteration of these two equations here, you have to do a Monte Carlo simulation and ensure that Monte Carlo simulation converged. So the core model, which is so far purely mathematical is solved using Monte Carlo. And once we infer the parameters, H and J, that better reproduce the sets while maximizing entropy, the Boltzmann distribution characterizes the statistics of the product activities of the cities composing a given community. So,
here.
Well, sorry.
Question
Okay.
here.
Danilo,
Sorry.
Danilo, I'm sorry.
Very interesting. Do you have problems with multiple solutions for the inverse sizing problem?
Yes, of course, yes.
And how much of a problem is this? Is that, are they all compatible in terms of the correlation functions and things like that? And of the results that you're going to get?
Yeah, in fact, it depends very much on the data set that we have. In this case here, we were very lucky. We were very lucky. Okay. So we had no metastable problems. We did it from different sampling of initial guesses. We tested very different configurations of the system, and we found something. Okay. Of course, the parameters may change, but as long as they replicate the observable data, and the thermodynamics that we see, thermodynamics under quotation marks, is consistent between themselves, it's okay. I'm sure. But of course, there are all types of problems, and BLEC has been working a lot on trying to develop new algorithms to improve. We are doing in our way as well things similar to that. So. But you're right, so it's not trivial to solve it. Anyway, so the first thing that you have to do is to learn the observables. So that's what you do. So this is what we had for the magnetizations of each city that we observed. This is the real data, and how it compares when the solution has converged with the data that the Monte Carlo procedure used. You have to remember that we have 73 spins. So we have 73 values of magnetization to compare and to match. And the match is perfect because this line here corresponds to y equal to x. Okay? So the learning is very good. Also for the pairwise correlations. So they perfectly match the observable and the Monte Carlo results. But now there is something which is, we have to prove that this model is compatible, because although we don't go to the third order, which would be the triplets of correlations, the third order correlations are there and can be calculated as observable. Okay? And we did that. And now we are comparing what the model with the parameters that we made the model to learn with the triplets that we observed in our simulations with the real data. And these are like that for the different communities as well as different categories of buying and selling. Okay, you see this is not perfect, but you have to understand that the triplets are not explicitly used in the learning process. So somehow, this Hamiltonian has some predictive property in terms of the triplets. There are other properties that we would have to choose, and of course there are many questions about the system is not being necessarily an equilibrium system. So, but what can we do? It reproduces, it learns the magnetizations, it learns the covariations, and it predicts the triplets of correlations. Okay? So.
Yeah, I'm just confused by the fact that you are still comparing the Monte Carlo with the observations. So you are playing the same game. You are able to compute the observables, and then you apply your Monte Carlo to do that.
Yes, yeah. I could compute observables up to any order.
Yeah,
if I,
sure.
But,
and then you
but I wouldn't dare to go far in the third order because this would be already a large, very large number of. Yes. Okay. But here is the game is different because T of ijk has never been used in the learning process. So and these are the types of things that we obtain in terms of the parameters. It's interesting to see that the correlations are all similar. They follow a Gaussian type of distributions. We use the Kolmogorov-Smirnov test to test it. And the local fields are mostly negative, but with some sort of asymmetry on the left side. Okay? Anyway, so these are the parameters that we have, that we learned from the system. And now, on the top of that, we can introduce ad hoc, in a very ad hoc way. I don't call it a different model. It's the same model, the same parameters. But now we can simply say that we are under quotation marks in the canonical ensemble. And we can introduce a parameter beta with the same partition function with beta as well. So, and the Hamiltonian will be like that. Okay, and then we can vary this parameter beta, which is 1/t in our case particularly, and see how the dynamics, how for instance, the macroscopic property of the system changes with this temperature of the system. Okay, and then that's what we see for buying, for the 3 largest communities, and for selling, for the 3 largest communities. We also did a test. I wanted to know if the fact, because we did it before I saw the movie of Mauro yesterday. Yeah? It was not from yesterday to today, because someone talked about a miracle, now that everything falls close to the maximum. It was you, Caroline, I think. No? I see it. Yes. So in our case, it looks like it falls very close to the maximum of the heat capacity, which would be the largest correlation that we have, and it's a near criticality. And I put an interrogation mark. But we did a test here, which is this line here. In this line here, we keep the magnetizations of every city in the system constant, and we shuffled the values of the spins. CTM has 1, 0, 1, -1, 1, 1, 1, -1, and then we shuffled, but the magnetizations are constant. So we basically we basically only changed the pairwise correlations. And then when you do that, you see that the system becomes, the operating temperature, which is arbitrarily equal to 1, becomes much larger than the peak of the heat capacity, showing that, in fact, by doing that, we are increasing the temperature of the system to a different state. But our operating state is the state of the system itself, okay, which is T equal to 1. Okay.
So you're suggesting that trades between municipalities is a kind of self-organized critical phenomenon.
Wow, so you did before that. Can I answer your question later, because you are spoiling?
Know that.
Okay. No, I'm joking, showing to you. So anyway, so I put Maradona. It was very hard for me to find which one of my soccer idols I would put, because I thought of Pelé, of course. But Pelé was kind of serious person. Also, I've never seen Pelé giving declarations in public. And then I thought about Messi. Impossible to see Messi in a situation like that, no? And then of the same class of universality in terms of quality, Maradona, I found, was the person who could say, why do we care? No? So thanks God, he existed, and I used to like him a lot. Apart from when Brazil lost against Argentina. The games were very tough for us. But anyway, so I wanted to show you a lot of, too many comments. But the first one is this model is derived directly from observer data. This I already repeated. But what I want to say is that it's not presumed as a simplified representation, because you have a match from the number of observations to the number of parameters that you have. So it's not merely a figurative or a metaphorical comparison that we have here. This model is not, it has some meaning, I would say. This is already said. Now we're talking about the temperature. What's the difference? Why our results reveal that each community operates at a temperature that is closing to the corresponding critical point. It suggests, as we said already, a high degree of economic cohesiveness. So there is something for buying and selling. And being close to a critical point is revealing, or miraculously revealing, since it is characterized by scale invariant fluctuations, blah, 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 and so on. And it should be on the verge of high sensitivity to both external and internal conditions. This might imply that minor changes in a single city might eventually disrupt large changes in the entire system itself. So these insights can be interesting to analyze economical systems themselves. And now the spoil of André Vieira, so Pierre Bach. So perhaps there is a way to analyze this in terms of self-organized criticality, which was originally proposed by Pierre Bach. And he said that complex behavior in nature reflects the tendency of large systems. But everything here is not critical, no? in this particular case, non-equilibrium system. He's talking about non-equilibrium. And we are using an equilibrium system. This is something that we could discuss, but I don't have time for that. I would like to show something else. Still have some time, no? Questions? Oh.
Well, this is not a good. This is not good for. I mean, if it's true, you know, that is near to criticality, that's not a good feature for an economic system, right? I mean, if you are able to provoke avalanches and I don't know, moving somewhere and then. Do you see it as a good feature?
I mean, it depends. There are different ways of. If you know what is going on, which is not the case now for the world.
Yeah.
We don't know exactly. We don't know nothing about what's going on now.
Right.
But if you have an idea of what's going on, you might adapt your system. And the chaotic system, as we know, is more easy to go from one state to another.
Okay. Yeah.
So
to adapt.
To adapt. So
yeah.
In terms of adaptability, this is what I meant.
Okay.
But,
yeah.
Of course, because the time of evolution of these systems, it's not so easy to implement an industry or to change completely the portfolio of products of a given city.
Yeah.
It takes time. So
right. But this is 3 years to also, right? You, do,
yes.
you could eventually, could you take slices of years
yes,
and see if
possible.
this approach
yes,
to this?
Yes,
yeah.
We didn't do that.
Okay. I think there's a question.
Professor, my question is because I wasn't thinking about this question, but when you mentioned about Mauro, that was about Mauro.
Model.
Mauro.
Ah, Mauro.
Yeah,
yes,
yeah,
yes,
about
yes.
the neurons, right?
Yes.
He made a very similar procedure and obtained exactly the same thing, the same. Yeah, I mean in the neurons. Yeah, exactly. So my question is, it makes sense. Your conclusions about the data, but you are sure that when you're training, when you are finding the multipliers, you are not the Monte Carlo is not choosing a model that is already in the critical point. There is not, I mean.
That's the same, very similar question that Danilo made, no, in terms of stability of the Monte Carlo method.
No, it's not exactly the stability. It's because
we changed, as I said to you. We did,
if you
several
if you give
trials
if you give a random data for this method,
that's what we
you
did.
are sure that it not will have this type of
this is the shuffling procedure that I showed you here. Maradona doesn't know to. So this is exactly your question.
Oh, I see. Perfect.
So we kept the magnetization of each city constant, but we shuffled for each city the spins for different products. For each city had his magnetization spins shuffled, but keeping the total magnetization invariant. So we were only changing the correlations, the pairwise correlations. And when we do that, the operating temperature, which is the operating of the system itself, is far away from the critical point. Critical, again.
Yeah. Thank you, Professor.
So this is somehow exactly to respond to your question. I had the same question. So.
One other question. All the data you process is within the same state, so it's all transactions between the municipalities inside one state, but they also exchange with the rest of the world.
No, we use for the products that's a very good question. For the RCA, we use the portfolio of all the products that have been exchanged between one city and every other city.
Even outside?
Even outside,
okay.
Yes. But for the calculation of the regions, we used only the internal transactions. Otherwise, it would be impossible for us to isolate the system. Okay. So we use what economists somehow called partial equilibrium, when they isolate a zone and calculate assets against demands. Is it okay? Can I go forward? Oh, there is another one.
So, just fast question. Do you think
no, please.
The distance of the peaks from T equals 1, especially for selling, is quite significant, right? We can see.
Especially for selling, yes.
Yeah. So, do you think that has some interpretation, like qualitatively with respect to how far the system is from criticality.
Oh, yes, yes.
And like, is there an interpretation you
Yes,
give us?
yes. How far is it from the? But you're talking about the system itself, no?
Yes.
This is less, more subcritical
Yes.
compared to the buying, no? So this has something to do with the explanation I gave for the density of the raster plot itself, which was very vague. But here it shows, in a way, that the cohesiveness in terms of buying is larger, no? Because then you are close to the critical point. But here it's subcritical, so the system is more cold than it should be compared to the critical point. So it's less cohesive. So the transformations are not so, the correlations are not so large. There is, we have a paper. It was a trial paper. I don't recommend that. See, I don't recommend my own paper because we didn't do everything that we had to do. I recommend it. I'm joking. So in which we analyzed, we have an eye tracker, and we analyzed people reading texts. Okay, and each time a person read the same word twice, we would put a spin 1, +1. Whenever it doesn't read it, -1. And we did it for different texts. And we found out that the distance to the critical point was a good proxy for the complexity of the text. Okay, for instance, we use texts that were generated randomly, but with perfect grammatical construction. And we use texts which were texts for children, very nice and simple, and they were completely opposite. The texts for children were very complex and very close to the criticality, while the texts which were generated randomly were very, very frozen. Okay, so that is, so somehow it shows it. It's a different index. Demonetize is a little bit more complex, but it is there. So shall I? So Maradona again, and let's go for something very different now, if I have time, Andre. 15 minutes, is it like 15 minutes, okay? Okay. So you don't know, you don't remember, most of you are too many young people here, but you didn't see Monty Python, did you? Carolina, you didn't see Monty Python. The British, really, you don't? So this is a good theme for the dinner tonight. So that's but the British are very, very, very special. The British humor is extremely special. So you're radical. But no, not even the slide you don't think, because it's completely different. Let's go forward. So this is just a comparison that I have used. I should use it before. How do we compare physical systems and complex systems? Particles interactions are essential ingredients. It's interesting that I like this concept because in the physical systems you see an inherent simplicity, although the talk of Eduardo today was not so simple in terms of the interactions themselves. But what you see at the end, because of the number of ingredients, you have phase transitions, pattern formation, and fluid turbulence, which are visible and identifiable. This is the opposite. Oops, sorry. And, okay, so this is a computational simulation that we did. It's a glass upside down with some very small number of molecules. I'm using a typical Lennard-Jones potential, and I make these particles. This is Gilberto Gil's talk. And then I wanted to go to social systems. Okay, this is an introduction to social systems, a comparison. So these particles, of course, they understand each other in a way from the potential, from the effective potential that they see. And of course, if they go very close, they repel themselves, and in the opposite. And of course, there are always the constraints of the glass, which is upside down. But eventually, you can identify, if they are close enough, immaterial connections, and see that there is a complex network that is formed and dynamically evolving inside the system. And this can be something related with social systems in the sense that we now have human beings, interactions, but opposite to the complexity of the ingredients. We are very complex people. So Carolina doesn't like Monty Python. I like it very much for complex reasons. But you can see regular behavior, for instance, consensus or polarized in opinions, emergence of a common language, and diffusive patterns governing the movement of people. So I like consensus, emergence of a common language, because it's funny to think that you are understanding what I say, and I think that you are understanding what I say, you know? And so it is, how can it happen? No? So it's a miracle. This is a miracle. No? Anyway, and then you can talk in terms of COVID. Hernan Max is my main collaborator. We published that paper in 2022. Nobody wanted to accept it. So why use COVID? COVID has this horrible stuff that the incubation time, the incubation time is larger than the latency. So before you express symptoms, you are already infectious. So that's what caused the burden and the chaos in the entire planet because of this. While the SARS-CoV-2 is exactly the opposite. When you express symptoms, you are not necessarily infectious. So because of that, it is very dangerous. In the first case, you simply isolate the person when that person expresses symptoms, and you cut the transmission. In the case of COVID, persons who were infected and infectious were walking around and transmitting the disease without knowing because they were not expressing. So this is what I wanted to say. So we did a dynamic contact tracing. We mixed two databases from cell phones, 257,000 mobile phones. We did it during the pandemics. And we combined that with anonymized data provided by the municipality of Fortaleza. We have very nice contacts there of people who were infected. And so we could match their phones with the place they live. Of course, we didn't know their names, but we could match these two databases, use this transmission time window, a probabilistic contact which depended on the time that these two people from the GPS were together, as well as the distance they spent together. So, and we could also gauge this probabilistic model based on the macroscopic situation of the city at that particular time. So we did that, and this is the type of things
just a
that
point.
sorry.
That's curious. Does Fortaleza had this amount of information about the pandemics, meaning that each one who got sick would call them?
No.
No. How do they have that? I mean, the databases too.
No, this database didn't come from Fortaleza. This was from a company that Hernan had a contact, Grand Data. This is the GPS.
But the other one.
Oh, this one we had in contact with the Secretariat of Health.
But how do they have this? People have to call them and say, I am sick. How do you know that people?
We could only use those that we had. They don't contact. They go to the hospitals and they're infected. And the SUS, the public service, were registering cases of COVID. So we had their names, but we didn't use it. It was anonymized, and we had their addresses. But we didn't use it. It's not very well located, with some approximation. So everything was in an emergency. But the address was not used. It was with a precision of 100 meters. That was, otherwise we couldn't match this with the telephones. And then these are the encounters. So as you can see, each spot of that means that two people got together. Okay, this was Fortaleza in the beginning. We did it for an entire state. Okay, and then it eventually spread all over the state and went to Sobral. And this is end of story. And then the pandemic spread all over the city and Brazil and the world. So, okay, so from that match, we could quantify those who were really sick after being contacted by others who were not yet sick. Okay, we had the line of time to do this, and we could identify the patient zero according to our list, and how did it contaminate the other patient which eventually appeared there, and from that we could gauge the model and calculate the hyperparameters of that. Do you want to make a question or to terminate my seminar, André?
Sorry.
Do you want to terminate? No? Okay, one minute, 1 second.
No.
So
you can go on for like five to 10
Oh,
minutes.
it's perfect, yes. So we have a complex networks of contacts. You know the complex. So each circle represents an individual, and each line that connects them indicates that there was a potentially contagious contact between them. And this is a hub. It's important, but it's not, as you will see, it's not necessarily the most important one in order to stop the pandemics. And we use for that, to calculate the position of the super spreaders, we use the K-shadow composition, which is a specialty of Hernan. If you don't know this, it's very simple. What do? You calculate different shells. You remove those sites that have the same number of connections, equal to 1 first. When you do that, you remove all of them. And now you still have sites that have connection 1. It's a bootstrap type of technique. Now you remove those which still have 1 again. And finally, you remove the last, which has only 1 connection. And then with this, instead of the degree of the site, you characterize the shell of the K-core. It's slightly different. So now you remove all of them who has 2 connections. And now you end up with the K-core of the system, which are the most dangerous and the nucleus of the infection, already talking about COVID. So this is the most connected side, again, and the layer with the highest K-core. So it's interesting, because Hernan had already made some papers in Nature Physics 2010, where he used the contamination model for K equal to 96, for this is the degree, and how the contamination spreads throughout the network, starting from this node with 96, but K-core 26. But when he did it for a K-core node with 63, this is the size of the contamination after the end of the bootstrap technique. So the K-core characterizes much more the infection and the length of the infection in the system than the degree itself. So these are real networks now. Before the pandemics, with the 7 K-core components here in different colors. So this is till March 19, from the beginning to March 19, and this is after the post-quarantine, so looking during the lockdown. Okay, so here we have different layers. People that were not, we have layer 0, which are the people that we could already detect as contaminated in the list of the Secretariat. And the other people were people we didn't know because they were not still in the list, but had located through GPS and had a contagious contact. So they could be flagged and called and say, okay, you had a contagious contact, potentially contagious contact. And from that, we could deconvolute and go back to geography and calculate where were the super spreaders during the pandemics. And the super spreaders were mostly, and unfortunately, in the hospitals. So the essential workers were contaminating a lot of people without knowing, of course. It's not their fault, and they could not abandon. But there were also super spreaders in warehouses, condominiums, and so on and so forth, but most of them were in the hospitals. So contact with super spreaders take place in high traffic areas, blah, blah, blah. Quarantine super spreaders was not a practical way to put them in quarantine because they were essential workers. You cannot quarantine a doctor if you don't know exactly that he's contaminated with exhibiting symptoms.
But how do you know that they were essential workers and not patients that were already in
hospitals?
Yeah, but they could be patients in the hospital.
Patients, yes. Patients, contaminating patients, but I suspect the super spreaders were other types of people, not only the K-cores. This is where I would like to go. But anyway, we could quarantine medical doctors and nurses and so on. I'm not blaming them. These are people that we know and then eventually got sick anyway. And, but there were these weak links that could be found out between super spreaders regions, you know. And these were most likely, these we could identify. These were most likely people that were working in 2 different hospitals. I don't believe they were patients going from one hospital to the other. So, and these people could be eventually tested. I mean, testing people which were essential workers would be easy, but not practical. But the optimal strategy that we found was to remove the weak links and to separate the super spreaders cores from one to each other. And now I finish with this slide here, talking about soccer. This is my Brazilian soccer team. Nobody knows. This is Santa Cruz from Pernambuco, if someone knows here. I'm proud. I'm not very happy. It's in the fourth series of the championship.
And when I was a kid, it was a very popular.
It was very popular.
Team.
Even Santos lost against them in 1972 when I was 10 years old. But in happiness and adversity, thank you very much. Sorry, too far.
So questions? So, I think Danilo has a question.
Yeah. So back to the inversizing problem. You started with data, right? And you had the description of the states, some sort of Ising states, and with some correlations given by the data. And you find the Hamiltonian, the interactions that would give the same kind of correlations in the system.
Yes.
And you did that without any temperature. You just had t equals 1, if you like.
Arbitrary, yes.
And then you make t different from 0, and you find that this is seems to be, if you calculate something like the heat capacity, seems to be critical or something like that, right?
Close to be critical, yes.
Can you take a step further and try to characterize the different phases this transition, this supposed transition is describing? Because that seems it's not exactly the traditional spin glass Hamiltonian, because the disorder elements there have different kinds of distributions and things like that. And we don't expect it to be a spin glass phase or anything like that. But can you say anything about the phases?
We tried because, for instance, we had samples from neurons from this Professor Plants, and to do that, to characterize that, you would have to have the same or similar system at different sizes, finite size scaling. You want to calculate critical exponents, I suppose, no? This is your question, no? No. This would be the fantastic achievement, no? But we tried that, and it was not very, very simple. We could not. So the algorithm in this particular case needs to be very, very, I think we need an experiment which is not biological, which should be more controllable. So that you keep the system, and you can do that for different system sizes and under very, very precise conditions of control. Yes, but of course, that would be very nice, yes.
Okay, there's a question here. And
Não, deixa ele perguntar primeiro. Tem pouco tempo. Depois eu pergunto para o Sara.
Okay, so Carolina is telling us that you can go first. No.
Okay. Okay. So the super spreaders must be the nurses and doctors, right? Because the patients are like sitting at the hospital for like a week if they have
very
COVID.
short time.
Yes, and they are leaving the hospital and infecting their
Very short time.
Yes. Okay.
Thank you for having me.
Okay.
It's tough to talk about the essential works. No, but I'm not talking badly. It's just a fact. No.
I just would like to understand, what are you calling super spreaders? Not the ones that I saw that not the ones that are more connected. It's more subtle than that. Can you come back and tell me?
The super spreaders, these are the K-core, for instance. This is the 7th K-core that have here. So these were people, after doing the bootstrap, people who had very small number of connections were being removed, and you eventually find the core from which you had, at the end of the bootstrap algorithm. These are the K-core ones. And this is, of course, this is a little bit biased because Hernan created this concept and used it a
No,
lot.
but I mean,
But as a matter of fact, it works into simulations using typical models of contamination of epidemiology. So he showed that.
Okay.
And
Okay, I see.
okay.
Oh, no, I see. Okay, but it's fair enough.
It's okay.
Just a definition.
Okay.
So
Professor.
you mentioned some strategy of how to handle the infection, the COVID infection.
Yeah.
But did you actually influence public policy
Oh,
there?
that is a very good question. We tried a lot. We had a lot of, we first, after we developed the algorithm, we put the algorithm in the pipelines of the Ceará government. And then they decided to make an app. There were, of course, there were not vaccine at that time.
Sure.
So they build an app, and then we start having trouble with the administrators. Because, of course, the fragility, I don't know, the sensibility of the data.
Sure.
So how to input that automatically to make that app. And also they didn't want to press people to answer very, very, very precise questions concerning to the participation of something, going to an event, or to flag people that they have been close to a contagious process. So they were not making the correct sequence of questions in the app. So it was on for something like 2 weeks, and they gave up. And then the vaccine appeared. But we tried very hard.
The app would be for tracing,
So yes, we made an app. We put it in the pipeline together with the algorithm. We put it in the government computers, and it started working. We announced. Some people used, and then they cut.
Sign of the times.
Yes, that's it. Okay, thank
Any
you.
more questions? So let's thank
Thank you very
Soares.
much.